Hey there, everybody. The purpose of this video is to get you some solutions to this fundamental counting principle quiz. So we did talk about this number and the number of ways to deal out unique decks of 52 cards. Yay. So the next thing up, hang on one second, shut my door a little bit. There we go. The next part is just says Google the age of the universe to the nearest billion years. All right, so let's do that. Age of universe. Okay, 13.772 billion years. We'll just call that 14 billion years. Even though technically speaking, we probably should use the precision that we're allowed to have, but that's totally fine. We'll just this is not really about the precision of that number. It's about converting that number into something a little more useful. So we'll call that 14 billion years. 14 billion years. Okay, number two, convert that time in number one. Convert that time in number one. That should say into days. I apologize. Convert that time in number one into days by multiplying it by that many days per year. So we're going to come up here. We're going to go 14 billion. This is actually pretty fun. 14 billion. And what's kind of fun is you can actually just go straight to seconds, but we're just going to do the math here. Times 365.24. And then that converts it into days for us. So that's how many days 14 billion years is. About 5 trillion. So the 5 is your operating number, and then this tells you how many zeros or how many places to move. So 10 to the 12th is trillion. 10 to the 9th, excuse me. Yes, 10 to the 9th is billion. 10 to the 6th is million, and 10 to the 3rd is thousand. So this is a number trillion. So 5 trillion days. Long time. 5 trillion days. Please convert it to hours by multiplying by 24, because every one of those days has 24 hours in it. So we're going to multiply that by 24, and that gives us a couple more decimal places of precision. So about 100 trillion hours. Okay, that would be hundreds of trillions. If 10 to the 12th is trillion, 10 to the 13th would be 10 trillion, 10 to the 14th would be 100 trillion. And then we're going to do minutes by multiplying by 60. So multiplying by 60. Okay. So now we've got, we're up to quadrillions now. So the 15th is quadrillion, so 7 quadrillion minutes. And then once more multiplication by 60 to get us into seconds. Times 60 into seconds. Okay, so now we are at hundreds of quadrillions of seconds. But if you think about it, that's still nowhere near the total number of card shuffles, right? This is the total number of card shuffles. 5 times 10 to the 67th. So that's if you remember correctly, I think that we call that an unvigintillion. So this is massive. This is massive, massive, not even close. I mean, it's 10 to the 50th different. That's a massive number. And what's interesting about this, and this is you got about half the quiz to hear, is that when I talk to people who kind of understand math, but a little conversationally, I tell them, they say, oh yeah, there's no possible way that if you went back and started shuffling at the beginning of the universe, there's no way that you would have gotten all of these numbers of card shuffles. But if you took a bunch of people back with you, you could. So in other words, if you weren't the only person shuffling, if you could bring friends back and give them decks of cards. So I said, well, how many? And what's adorable is they say something like, well, like maybe 1,000. Okay. So we're going to go way more than that. We're going to go way more than that, because 1,000 won't even put a dent in it. Let's get totally ridiculous. Now what I want you to look at, this here. Okay, this is essentially what your first project is going to have you do, which is converting from one unit to another unit based on what are called these conversion rates. So you can read through this bit right up here. I made some assumptions. I watched a video about how bicycle playing cards are made. Really cool, actually. I didn't know that they came off of rolls. Really rad. And I took all the numbers essentially that were in the video and upscaled them by quite a bit. So I said bicycles have been around for about 150 years, so we went with 150, which is actually longer than they have. That's how many days are in a year. We totally converted that. And then I noticed that they also said they can do something like, I think it was 11,000 decks per roll, so I made it 15,000 just to, again, upscale it to overestimate. And I couldn't get a count, so I just overestimated with how many rolls a day. And I assumed that they work every single day of the year, which probably isn't true. They probably don't work on weekends, but what the hell, let's make them work every day of the year. So if you multiply all those together, what you might notice is years and year cancels. Day and days cancel. Roll and rolls canceled, and you're left with just decks. And that is the point of dimensional analysis. We've started doing it in class a little bit with grade. We're going to continue doing it tomorrow with more grade. So you're seeing this idea of converting. You can convert 150 years into 41 trillion decks of cards by simply multiplying all this out. And then I said, let's overestimate. And I said multiply it by 1 million. And then I just said, let's just call it something even bigger than that, and 50 quintillion. So let's remember what 50 quintillion looks like. 50 trillion. A trillion is times 10 to the 12th. Quadrillion would be 10 to the 15th. A quintillion is the next one. It's going to be 10 to the 18th power. So this is 50 times 10 to the 18th power. That's a huge number. Again, not huge like this, but huge. So now this question right here, I want to walk you through this one right here, because I did ask you to show work on this one. We are going to take every one of those 50 quintillion card decks, and we're going to give each one of those to a person at the beginning of the universe. We have completely left the realm of possibility here. We left it a long time ago, but we're totally leaving it now. And even if you took 50 quintillion people and let them each shuffle a deck of cards 1 per second, you still wouldn't even be close to this number. So I'm going to walk you through the math on that one now. All right, so we know, I'm going to create a little set of equations in Word here. Now I'm going to talk you through this as I type. If you ever want to make fractions in Word, this is a way to do it. It's kind of old school. There's easier ways to do it. This is how I do it. You know what? I'm not going to talk you through it. If this interests you, send me an email. I'll make you a video explaining it. So I'm just going to make this real quick here. Fraction. Okay, so we are going to have 50 quintillion people, each with a deck of cards. And then we're going to put that over 1. I don't think I shouldn't use parentheses. I should use commas. Okay, so this makes a fraction right here. So I've got 50 quintillion people, each with a deck of cards, over 1. Times. Now here's the, well, let's make an equal sign. Let's actually write that out with all the numbers. I think that might be helpful to see, right? Actually, to see all these numbers. Toggle. So 50 quintillion is going to be 50. Let's make sure we go through this. 50,000, 50 million, 50 billion, 50 trillion, 50 quadrillion, 50 quintillion. There we go. Okay, so that's what we've got. 50 quintillion decks of cards. Okay. Now, what we are going to do is, every second, we are going to shuffle those decks of cards, and then we're going to have to bring in the number that we calculated from before, which I hope I saved. I think I did. I did. It's right here. This is how many times those decks of cards get shuffled in total. So each one of those decks of cards is going to be shuffled this many times. Okay? Every one of these decks of cards. Okay, I'm not even sure why let's just take this down here. 50. 50 quintillion decks of cards, each shuffled 400 trillion times. So I'm just going to leave this number here and write it out in words here for a second, because we're going to use Google to actually crunch the math. Each shoveled 400 or 4.17 100 trillion times. Yeah, I think that warrants not only a smiley face but some exclamation points. So each one of those decks of cards, each gets shuffled this many times. So if it was just one deck of cards, it would be 417 trillion times. If it was two decks of cards, it would be twice this. It would be 8.34 trillion times. If it were three decks of cards, it would be about 12 and a third trillion times. So if you think about it, it is once again the fundamental counting principle. If you can do this many times, you can choose a deck of cards 50 quintillion ways, and then the ways they can be shuffled this many ways, the way to figure out the total number of shuffles or deals or however you call it is going to be by taking that 50 quintillion decks and multiplying that by the 4.17 trillion shuffles per deck. So if you want to think of it from a dimensional analysis point of view, here I'll bring this down here and prove to you that this all works. It's 50 quintillion decks of cards times, what I'm going to do is I'm going to do some typing here for you, times 4.17 trillion shuffles per one deck. Now what you're going to notice is, math-wise, you're going to multiply 50 quintillion by this 4.17 trillion. That's totally great. But unit-wise, the decks here and the decks there cancel, and you're left with just the unit of shuffles. So what we can do is we can keep that in mind and walk over here and then multiply all of this by 50 quintillion. Let's spell that right. Quintillion. Okay, here we go. Here we go. So 14 billion years times 365 and a quarter days in a year, years cancel, times 24 hours in a day, days cancel, times 60 minutes in an hour, hours cancel, times 60 seconds in a minute, there we go, seconds are left. Then you've got 50 quintillion decks times all of that mess. Oh, I apologize for that little typo that was back there. I got a little too busy typing with the 8. Here is what we end up with. 2 times 10 to the 37th. Okay, so we're just gonna try to write that number out because I can't even envision what that is. So it's 2 times 10 to the 37th. So it needs to have 37 zeros after it. 32, 33, 34, 35, 36, 37. All right, got them all. Let's zoom in. Let's go back. 1,000, million, billion, trillion, quadrillion, quintillion, sextillion, septillion, octillion, nontillion, decillion. And now we're past decillion. And I don't know what the next one is. We're going to call it 11 tillion. Because I don't know what it's actually called, and I don't want to look it up because we got too much information right now. But this is the total number of shuffles. But compare that number, which only has 37 zeros after it, to the total number of shuffles that has 67 places after it. We still haven't even really put a dent in what is there. Still haven't even put a dent in what is there. I mean, it's impossible to even kind of understand because these numbers are so big. But once again, this number is so much bigger than this number you just calculated. And here's, let me see if Google can handle this. I bet you it can. If I divide the actual number of shuffles by the number we just got, it can handle it. That's how many times too small it is. So I just divided the number we just got into the total. That tells us how many times too small our number is. 10 to the 30th is a decillion, I believe. Is that right? No, 10 to the 30th is going to be, so cubed is 1,000, 6 is million, 9 is billion, 12 is trillion, 15 is quintillion. Yeah, I think it is decillion. Sextillion, septillion, octillion, nonillion. Yeah, I think it's decillion. You're off by 3 decillion times. It's ridiculous. Which means even with that many people shuffling, an impossibly large number of people shuffling an impossibly large number of decks, you still can't even put a dent. You still can't even put a dent in that number. And that is fairly staggering. So that was the point of this quiz. It was kind of to make your mind kind of explode a little bit. And that's why I put big numbers are hard to imagine, because they sure are. But nonetheless, we have ways to measure them, which is the important part. Okay, hope that helps. We'll see you in class.